Hello, this is our second lecture on chapters 1 and 3. Today, we're going to be talking a little bit about units, which is chapter 1. Um, that's mostly information. And then we're going to talk a lot about vectors in much more detail than we talked about on in the math skills video. So, in fact, in the end of next week, I believe we're going to do a um, vector lab, which is primarily everything you need to know in here um, will be useful for that lab. So you might want to go back and make sure you know how to do this. That lab is kind of long and a little awful, but it'll really, really help you get your skills down adding vectors and understanding how to add vectors. But today I'm going to try to talk to you about how vectors add and subtract and multiply and give you actual examples of what we're going to do with them in our course. But I'll talk more about that in a minute. Let's start with chapter 1. Um, Chapter 1 is, as I said, all about units. In our course, we're going to use scientific um, SI units, which means we're going to have to always keep our units in meters and seconds and kilograms. All other units, newtons, joules, pascals, are formed from those three quantities. And I want to talk a little bit about how you can relate those quantities to what you know. Unfortunately, a lot of us aren't used to the metric system. And if you're used to the metric system, great. But a lot of us are used to feet and pounds. So I want to talk a little bit about each of the units of measure, where they come from, and pretty much how you'll see them. And then I'll give you some kind of rule of thumb uh, conversions so that you can, in your head, understand like how fast is a meter per second, how heavy is a kilogram, those type things. Okay. All right. So the unit of length that we use in SI units are called meters. Um, we'll often go to centimeters or millimeters. Those tend to be useful for measuring everyday objects. A meter is essentially a yardstick, so it's about a little more than 3 feet, but 10 centimeters will, ordinary objects like a piece of paper, could be measured in centimeters. Millimeters are good for measuring smaller things like, I don't know, um, a coin in your pocket. You might use millimeters or centimeters. Centimeters are 100th of a meter. Millimeters are 1,000th of a meter. Often in biology, if you're doing biology, you're going to go down to micrometers. If you're doing chemistry, you often are in centimeters. Cubic centimeter of volume has the same volume as a milliliter. And then basically the other thing that we see are nanometers and light, visible light anyway. The wavelength is usually in nanometers. Well, is in nanometers for visible light. So that's kind of the length scale that we're going to be on for a lot of our problems in this class. We have to have things in meters. If we don't have them in meters, our numbers will be wrong. In general, the problem you're going to find is a lot of the labs we do will actually be measuring things in centimeters. Measuring something falling 80 centimeters is a little more than 2 feet, like in the free fall lab. And then you'll forget that you need to convert from centimeters to meters, or your constant of gravity will be wrong. It'll be off by 100. And we'll talk about that when we do those labs. But for now, just know that you need to get used to everything being in meters, and you kind of need to understand how long a meter is. In the old days, they used to measure a meter as a specific block. They had a specific block that was a specific length. And obviously over time that'll wear down or could change with temperature, whatever. So now we use the wavelength of a specific color of visible light. I don't remember what that is. I think it's some kind of red light. That is always a constant length, and therefore it serves as basically the measure of a meter is so many of these wavelengths. Highly accurate. It should be the same anywhere. So it's a much more accurate way than just saying, oh, your foot. There's a kind of funny story about the foot, you know, in imperial units or whatever. It used to be that a foot was as long as a king's foot. So every time you got a new king, measurements changed. That's not helpful. We need a unifying, constant measurement so that everyone's observations will be the same. So that if I say 10 meters, you would also measure 10 meters. And so that's what we have. We have the wavelength of light is the same for everyone. And therefore we define what color light, we get the wavelength, and that tells you how long a meter is. The next thing is time. Time is obviously in seconds. You'll often see it in milliseconds, which is 1,000th of a second. That tends to be about as fast as we can really understand or observe things. When things get much faster than that, they're too fast for human observation. We can use cameras and things like that. But the funny thing about time is you have to be really careful. We measure seconds in tenths of a second, in hundredths of a second, in thousandths of a second. But when we go the other way, we tend to go up to minutes. And minutes are 60 seconds, which means that you always have to convert into minutes, hours, years. And that 60 seconds is kind of a weird unit. It's basically seconds or metrics, or use the metric system, base 10, as you go down. But as you go up, they're in this weird 60 second intervals, or base 60 or base 20. That's a little odd, but it has to do with the way we measure our clocks. It's left over from other systems of measurement that were used. For example, the Maya, their system was based around 20, not 10. It's worth checking out. It's a pretty neat way of counting, but basically you count in units of 20, not units of 10. And we kind of do that with seconds. So you have to be careful. It's weird. There's no unit of 100 seconds, but that's okay. We know how to deal with it from everyday experience. The other thing that you need to understand is when we talk about time, sometimes we talk about the exact time, something happening at 9:02 and 2 seconds. But often when we write time in an equation, what we're really talking about is a duration. We're expressing time, t, as basically a delta t. So t is really a delta t. And whenever you write a delta, you write final minus initial. But we're assuming that the initial time was 0 and we counted some duration, some like 20 seconds, let's say. So our final time is 20 seconds and we just write t is 20 seconds, okay? That's pretty lazy, but you'll see our book does it. It does it during the constant acceleration equations. It does it during projectile motion. You almost always assume that time initial is 0. And that's just something that happens. As I note here, physicists are lazy. It's a lazy idea. And it's something that you need to remember is kind of being ignored, but you sometimes will need to understand that you're talking about T final minus T initial, which is a little weird, but it almost never comes up. But when it does, it's pretty obvious that you've got a duration. Anyway, we'll talk about that if it ever comes up. I can't imagine it ever coming up. It might come up in one of the labs when we're taking the time of periods, oscillating motion. But now we kind of use the Earth as our time, as our clock, because we're biological creatures and we know how long a day is, and you kind of measure a day in hours and an hour in minutes and those seconds. But the Earth itself is a really inaccurate clock. Time changes based on a lot of things. Earthquakes can actually cause the rotation of the Earth to slow down, making the day longer. Just clocks wind down. And therefore, to get a constant value for a second, what we actually do is we use atomic clocks. And we know that atoms vibrate at a certain speed. And therefore, we can use that speed to give us the duration of a second. And so an atomic clock is highly accurate. Things need to be very accurate because of relativity. When we talk about relativity, basically, you need to make sure everything can measure the same time, or you need to know how the time's different. If you don't get what I mean, there are satellites up in space that basically are setting your clock. And those satellites need to know an accurate time count in order to send the time to your phone and make sure that it's right. So essentially the unit is seconds. We'll often go down to milliseconds, which are thousandths of a second. And we use atoms, the vibration of atoms, to set what is the standard length of a second. And then just remember that when you see T in an equation, it oftentimes means T final minus T initial, but T initial is being taken as 0, okay? The last fun one is mass. Mass is the final unit. Mass in SI units is kilograms, and that should automatically tell you, why is the name 1,000 grams? Well, chemistry uses grams. Grams tend to be easier or they're more useful quantities. When you cook a recipe, you might use a tablespoon of sugar, but that will be a couple hundred grams of sugar. You're not using kilograms. Kilograms are actually quite heavy. You might measure like a hamburger in 2 kilograms, but in general, for precise measurements, you're going to be in grams. You're going to be in thousandths of a kilogram. However, in newtons, the unit of a newton, which is a big N, is a kilogram a meter per second squared. We measure mass in SI units in kilograms, which leads me to my next point. What is mass? And I want you to stop and think about that. Some of you may know the answer. Some of you may think you know the answer and you're actually wrong. We say objects have mass, but we often confuse it with weight. Your weight is actually your mass times gravity, but gravity can vary. Turns out that gravity varies by the distance between two objects squared. So the gravity on the surface of the Earth depends on the mass of the Earth and how far you are from the center of the Earth. If you go up a mountain, gravity becomes less. If you go down into Death Valley, gravity becomes greater, you're closer. And therefore, you weigh more at the bottom of a valley than at the top of a mountain. You weigh more at the surface of the Earth than on the moon, dramatically so. If you go to Mars, you weigh a lot less than you weigh on Earth. So mass is not weight. What is mass? Well, there's two ways to see it. One is imprecise, and the imprecise definition is basically how much stuff there is. So if we say a mass of a gold bar, we mean how many gold atoms there are, in a way. But the better definition is how Newton used it. And Newton used mass as basically a quantity that defined how hard it was to accelerate an object. And you can see that in Newton's famous equation, F equals ma. If we solve this for acceleration, acceleration is the change in speed or velocity of an object, we see that the acceleration is the force divided by the mass. So for the same force, if you have more mass, you are accelerated less. And if you have less mass, you gain greater acceleration. What this means is I can push a ball of paper. I can crumple up a ball of paper. I can push it with a light force, and it flies across my table. It gets accelerated really fast. If I try to push a heavy brick with that same force, it may not go anywhere. So what mass actually is it's your resistance to having your motion change. And that's something called your inertia. It's your inertial mass. It is how much stuff, the more mass, but it's constant. You have the same mass on the moon as you have on Earth, as you have on the other side of the galaxy. It's an inherent property of matter, which you need to make sure you understand. We measure that mass in kilograms and sometimes grams. There's something called the CGS system, which is centimeters, grams, seconds. We'll talk a little bit about that. We've already seen it with the density of water, which leads me to density is mass over volume. So what density teaches you or tells you is how much stuff there is in a unit of volume. So basically, imagine this as you could have, I don't know, like 1,000,000 water drops in your water bottle, and each of those water drops has 1,000,000 molecules of water. So the density of a drop would be 1,000,000 times, or 1,000,000 divided by 1,000,000 drops divided by the volume. Basically, what I'm trying to say is that density is a unit measurement of how much stuff there is in a particular volume. We'll talk about density way later when we talk about fluids. I think you all know what density is, but just remember that density is usually written as a little rho, and it's the amount of total mass over total volume, or it's also infinitesimal mass over infinitesimal volume. In this class, we will almost always assume that no matter what the object is, it has a constant density. Different objects will have different densities, but for instance, water will always have the same density. Gold will always have some same density throughout it. Um, it's not very physical, but we're going to assume that everything has constant density. And then the last thing I'm going to say about mass is, how do we define what a kilogram is? Again, in the old days, they had a specific block of metal that was 1 kilogram. But now, since we can measure the weight of atoms, we measure carbon atoms, and a carbon atom becomes the standard for a kilogram. We know how many carbon atoms would be in 1 kilogram, and so we can take the weight of 1 atom and multiply it by enough to get a kilogram. And that's pretty easy to understand. So our 3 units are kilograms, meters, and seconds. We use those to make up every other unit. Newtons are kilogram meters per second squared. Joules are newtons per meter, or newtons times meters. Pressure is force over area. It's newtons over meters squared. We'll talk about those as we go. But all units in SI are built up of these 3 fundamental building block units. And so just make sure you understand that if you're given, I should note that Wiley Plus loves to give you things in the wrong units. They'll give you something in grams and centimeters and ask you for an answer in newtons, which means you're going to have to convert. And those conversions are super easy. You know how to do them. If you have something in grams, let's say you have 10 grams, there is 1,000 grams in 1 kilogram. So obviously 10 grams is equal to 0.01 kilograms. 10 divided by 1,000, and the grams cancel. Similarly for centimeters, although there's 100 centimeters in a meter, you guys should know how to do that already. If you don't know how to do that, make sure you practice it a little bit. In general, when you're doing Wiley Plus and you get the answer wrong, the very first thing you need to check is, did you convert your units correctly? Are you in meters, seconds, and kilograms? Because usually you're not. That's usually the first problem you have. And unfortunately, I don't like that Wiley Plus does it, but they really, really like to try to trick you with that bit of information. All right, so the last thing I'm going to give you is something that I like to call useful ballpark conversions. And so what it comes down to is, well, what is a meter? If I told you something was 10 meters long, how long is that if you're not used to metric units? A meter is about a yardstick. It's actually closer to 3.3 feet. So in general, I go with about 3 feet. I'm 6'3". I'm about 2 meters tall. If something's 4 meters tall, it's about 13 feet high. That's pretty high. 4 meters is pretty high to humans. Football field, which is 100 yards, 300 feet, is about 91 meters, okay? And therefore, when you're going through these problems and they say something falls 2 meters, you know that it fell about 6 feet. Another thing that we always talk about is, a lot of times in problems we'll say that an object's traveling at 5 meters per second. And is that fast? Is that slow? Well, it turns out it's almost the same for converting from miles per hour to meters per second and converting from pounds to kilograms. If you multiply meters per second by 2.2, you'll get the speed of miles per hour. So what that means is about 14 meters per second is around 30 miles per hour. You guys should know how fast that is driving in your car. A baseball is thrown at 80 miles per hour. That's somewhere around 40 meters per second. It's more like 37 or something. But yeah, 37 meters per second is about 80 miles an hour. That's really fast. 2 meters per second is only 5 miles per hour, but it's about the speed that a human will walk. So walking speed is about 2 meters per second. Just keep those in mind when you're analyzing whether or not your answers make sense when you do these problems. If you find that a human was running at 300 meters per second, obviously there's no way a human is running at almost 610 miles per hour or whatever. You know you've done something wrong. The nice thing is that we're in the real world, and therefore answers should make sense, and you need to have some kind of intuition about how fast, how long, or how high, or how much things weigh. As I said, you can also convert from kilograms to pounds. So let's say you weigh 140 pounds. That roughly turns into about 64 kilograms. Multiply 64 by 2.2, you get around 140. So I don't know, 2 kilograms is about 5 pounds. If you understand what 5 pounds is, more precisely, about 40 kilograms is pretty close to 90 pounds. So 42 kilograms is about 100 pounds. That doesn't come up as much. We almost never really need to think about how much things weigh, but it's useful if you want to know. If you want to know that 5 kilogram object that we're talking about weighs 11 pounds. So anyway, there won't be any homework on any of this chapter 1 stuff. It's more for you. It's more information. It's stuff you need to be comfortable with if you're not comfortable with metric and SI units. But you'll get comfortable as we go. Just keep it in mind. It's important that you know it. It will come up in Wiley in your homework. You will more than once probably make a mistake where you've got something that was given to you in grams and you forgot to turn it into kilograms. The first thing I would always do, I would just recommend it, is get used to converting everything into meters, seconds, and kilograms if you can. Sometimes Wiley won't ask you to convert it, which is really annoying. But for like our labs and stuff, it's useful to turn things into meters, seconds, and kilograms before you do anything else. However, assuming you all go into science, you're biologists and chemists, when you're displaying your data, you often want to display it in a useful graph, and that's often a scale of centimeters. So just know what scale you're in, and remember that things like force are in kilograms, meters, and seconds squared. So you're going to have to convert them when you're talking about force. But we'll talk about that later. That'll come up as it comes up. I will tell you that I'm not really big on trying to trick you on an exam. I'm almost never going to give you things that are in grams or centimeters. And if I do, I will also give them to you in meters or kilograms. If I tell you that an object falls 2 centimeters, I'll say 2 centimeters or 0.02 meters. So you'll be given the units converted. I don't believe in tricking people that way. I don't think it teaches me a lot about like your skills as a student that you can convert from centimeters to meters. But Wiley Plus thinks it does, so it does it a lot. I can't change that, unfortunately. If you're getting a question wrong, make sure your units are correct before you do anything else. So now we're going to talk about chapter 3, vectors. And this is really, really important that you understand why we use vectors, why vectors are the language of physics, and then how to turn vectors into math, into mathematical notation so that you can use them in an equation. So let's talk a little bit about drawing motion. And I want to start with a ball. Let's say I throw a ball upward. It goes up, reaches the top of its motion. It briefly has no velocity and comes back down. So when I draw it, it goes up and comes back down. I'm going to assume I'm only in one dimension. In fact, I'm going to assume that this is the positive y direction and this is the positive x direction. You almost always should, as a first step, whenever you draw anything, assign a coordinate system, whatever coordinate you want. In this case, it makes the most sense to me to call y positive up and x positive to the right. That's preference. I could change that in any way that I want, but that's what I'm going to call. So if I want to describe this motion, how do I do it? How do I take my drawing of a ball going up and down and turn it into a math equation? And how I do that is at each specific time, I draw a vector. And I want a vector, I actually want two vectors. I want a vector that shows its velocity. So initially its velocity is up in the y direction. And there's an acceleration due to gravity, which I'm going to call g. It's not really important that you understand anything about what these are, other than what I'm doing is I'm drawing these vectors in order to understand the motion and to be able to write a mathematical equation of the motion, okay? As this ball goes up, it loses velocity, and the velocity becomes less and less. When it gets to the top of the motion, it has no velocity. As it goes down, the velocity changes and is now in the negative direction. And as it falls further, its velocity increases, okay? So as I'm drawing at each moment in time that I'm interested in, I can draw a vector that shows its velocity at that moment. How long the vector is tells me the magnitude or the value of the velocity. The magnitude is decreasing up to the top of its motion and increasing as it falls back, but increasingly negative, okay? So I basically have this picture that looks like this. V, 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 0, down, down, down. And each of these is a velocity vector at a specific time. So that could be time 0, time 1 second, time 2 seconds, time 3 seconds, 4 seconds, 5 seconds, 6 seconds. The entire time is going to have an acceleration in the negative y direction of g. And then I can turn this picture into a math equation using these vectors. Now, the visual representation, as I said, is you draw an arrow. You have to have some kind of coordinate system. So again, positive y up, positive x to the right. So this is my vector. And let's say that I've defined this as 2 meters per second, because I want this to be a velocity vector. No matter where I put this vector, as long as I don't change its orientation, it's the same vector. I know I'm not drawing them exactly the same, but as long as these all have the same magnitude, and we write with this little funny hat, which just tells us that it's a vector, as long as I haven't changed its direction in relation to the y-axis, and I haven't changed its magnitude, I can do whatever I want. I can move it wherever I want. The other characteristics that a vector has is it has to have a tip and a tail, or a tail and a tip. And that means that basically This is a positive vector if I go from the tail to the tip. If I travel the direction that it points, it's positive. If I were to travel from the tip to the tail, and we'll talk about this more later, I actually am traveling in the negative direction and I get a negative vector. So the same vector is negative if you just flip it. You flip its direction 180 degrees. That is equivalent to multiplying it by a negative sign. Further, if I want to multiply this number, if I want to make 3a, right, I would just have 3a, right? So this is a and a and a. So this is basically what's known as multiplying a scalar times a. Scalars are just numbers, and scalar multiplication of a vector works exactly like multiplying any two numbers. It just multiplies the entire vector by a certain quantity. Here. Sorry. Yeah, so we have this visual representation of a vector. You can pick a vector up and move it wherever you want, like it's a refrigerator magnet. As long as you don't change the direction or the magnitude, it's the same vector anywhere that you put it, as long as it doesn't change its direction. All right, so what's weird about vectors is that we often write them as something like A. But what we mean is something totally different. We can write A plus B. But what we really mean is we mean all the components of A. So we have, in component form, A has X plus AY plus AZ plus on and on and on. For those of you who are in computer science, you'll understand that a vector actually can have as many components as you want. The columns in an Excel spreadsheet are vectors of the data. For us, we're going to be talking about motion. And so our components are going to be in the X, Y, and Z direction. And generally, we're almost never going to need the Z direction. We're going to need the Z direction for rotation, which you'll see at the end of this. But most of our motion will take place in the Y and X. So we won't need this. But just know that the actual definition of a vector can have as many components as you want. You can have an infinite number of components. And in fact, a lot of information can be presented as vectors. When we do labs, our error is actually kind of like a vector. And how you see that is the magnitude of a vector is the square of the components summed. So what that means is you take AX and you square it, and you take AY and you square it, and you take AZ and you square it. And you just add them all together, take the square root, and that gives you the magnitude of A. And it's often, it's really easy to confuse the magnitude of A with A. I mean, we're kind of saying A plus B, and B has some other magnitude. We'll do an example of this, but it's not actually correct to do that. I mean, it is, but it isn't. I'll show you as we go. But just know that when we say A, we mean the components of A. And when we say the magnitude of A, we mean the length of A. The magnitude of A should be positive. it's absolute value. We'll talk about that as we go. So the reason why we need components is we need to be able to add two vectors. And the easiest way to begin to see that is a really simple example. Imagine you start at your house, which is our origin, and we're going to have positive y, and we're going to have positive x. So you start at your house, and you travel 2 blocks east, I guess, and then you travel 2 blocks north. And what I want to know is how far away at point R are you from home if you do that? So what I can say is I can say that this is a vector A with a magnitude of 2. So the magnitude of A is 2. But the components of A actually, you can see, only has a component in the x direction. So it has an AX plus an AY, but AY is 0. It has no part of it that goes in the x direction. So that's 2. The little x hat tells you that it's 2 in the x direction. Unit vectors, if you multiply 2 unit vectors together, x times x is 1, x times y is 0, x times z is 0. It's just a convenient way to note what direction we're talking about. If you study the math of vectors and vector analysis, you really have to pay attention to your unit vectors. We don't in this class. What we need to do is we need to make sure that we know what component we're talking about. In this case, AX is the component in the x direction of A. Another way to see this is that any vector, right, at any angle, so a vector H at some angle from the x direction, H of x is the x component, and H of y is the y component. H of x is H cos theta, and H of y is H sine theta. We've already gone through that. But A is a vector that lays along the x-axis, so theta is 0, and sine of 0 is 0. Sine or cosine of 0 is 1. Therefore, this is actually A cos theta and A sine theta, where A is 2. It's actually that if you want to write it that way. Because theta is 0, this becomes 1 and this becomes 0, and therefore you get A of x is A in the x direction. Okay, we'll do more of that in a minute. We can also see here that B is a vector that lies along the y-axis only, right? And so therefore it's 2y hat. So we have 2 vectors. This one is our A vector, and it's 2 blocks, and this is our B vector. And we want to add A and B. So how I'm going to do this is, I'm going to actually walk them. I'm going to do this in a kind of clever way. I'm going to walk them. And what I mean by walking them, again, y and x. If I walk a vector from tail to tip, I get positive A. So I get positive A and positive B. So I write down A plus B, okay? And now what I want is I want to draw what's called a radial vector. This is what I originally wanted to know, was how far from home my distance was when I got to this point. R is what I called it. And so I need to know what this radial vector is. So I walk A, I walk B, so I get A plus B, and then I'm going to walk back home. Well, I'm traveling from tip to tail. So if I'm going this direction, I'm actually getting a negative r. This is r, this is negative r. So as I walk from this point back to home, I get a negative r. And I know that when I get home, I haven't gone anywhere. So this becomes 0. And what you can see from this is you get a plus b is equal to r if I move it, right? That's how you add vectors. It's a visual representation of how you add vectors, but that's how you add vectors. If I have any two, so let's say I have an A and a B that points in some other way, and I need to add them, I start at the tail of A, and I draw an arrow to the tip of B, and that's my resultant. And then if I walk, A plus B minus R is 0. So A plus B is R, is my radial vector. Secondly, what you need to know is that the components, well, we'll do that next. So the magnitude of the resultant vector. So the components of R is just like A and B, Rx plus Ry, but Rx is R cos theta of R, and Ry is R sine theta of R. And we're going to draw this again. So we have A and we have B, and then we have our R, and this is theta of R. It's the angle that R makes with our x-axis, okay? And so now if I want the magnitude of R, I know that it's Rx squared plus Ry squared. But what are Rx and Ry? Well, it turns out they are just the components of Ax plus Bx. And these are the components of Ay plus By, okay, in the X and Y direction. Now remember that we said A was only in the X direction and B was only in the Y. So this is particularly easy. And I get that R is, well, the magnitude of R. I'm going to write the square root the more typical way. So 2 squared plus 2 squared to the 1/2. And that becomes 4 plus 4, which is 8, square root of 8. If I pull a 4 out of here, I get 2 root 2. So my radial vector is 2 square root of 2. It's exactly as if I had a triangle with an x length of 2 and a b length of 2. But remember, what we're trying to solve here is we want to know if we walk to the store and we go 2 blocks east and 2 blocks north, how far from home are we? And we found that that radial vector is a plus b, and it has a length of 2 root 2. Now it's probably obvious at this point what the angle of R will be, but let's show how to do it. Now, in a normal triangle, right, H, X, and Y, tangent of the angle is Y over X. And therefore, if we want to know what tan of theta R is, we would take Ry over Rx. And if you really, really want to see that, you already know that Ry is R sine theta and Rx is R cos theta, or this is theta R. The R's cancel and you get a tangent there. So this is true. But we know that Ry and Rx are 2 and 2. And therefore, what we have is we have tangent is 1. And arctan of both sides here, if I take the arctan of both sides, what angle of tangent is equal to 1? Turns out that there's only one. I don't know where my calculator is for some odd reason. Let me grab my calculator. Our tan of 1 is 45 degrees, obviously, or 225 degrees. But yeah, so you know that the angle has to be, the angle of the resultant vector is 45 degrees. So, okay, so let's really quickly go back through and talk about what we've done. We have a vector, r, and that vector is equal to a plus b. That vector can be represented as components, rx and ry. These components are actually r cos theta r and r sine theta r. Furthermore, these components are ax plus bx from this equation and ay plus by from this equation. And finally, we have the magnitude of r is rx squared plus ry squared, and the angle of r is arctan of ry over rx. And we had, this was a pretty simple example, but we've already got a whole bunch of work there, which is pretty crazy. These vector additions can get really complicated, but there's a few really nice things about them. First of all, so there is the idea of, I'm forgetting right now what, which of the properties it is. So one thing that we need to talk about here is that you're in math so far, you've done all of your math in the real numbers, as we like to call them. And real numbers have certain properties, but vectors are a brand new set of mathematical objects, and certain rules apply and certain don't. And one of those rules, I believe, is associative. Is it associative? I'm sorry, the mathematicians will correct me, and I'm so sorry if I've got this rule wrong. Or commutative. I believe it's the commutative. No, commutative is multiplication. So associative means that does a plus b equal b plus a? And in real numbers, 1 plus 2 is equal to 2 plus 1. But here, in vectors, does it? Well, it turns out, yes, it does. It doesn't matter the order, because here you get ax plus bx plus ay plus by, right? And these are your x and y components of whatever this happens to equal. This would be the same, except by and ay would be flipped, and so it doesn't matter. Therefore, the order of addition doesn't matter. I can prove this to you another way. So in our idea, we walked to the store, right? And then we, let's say, walked home. But when we walked home, we went a different route. So A, B, C, and D, all vectors of magnitude 2, different directions. A is positive x, B is along the positive y, C is negative x, D is along negative y. Now, I can do any order of A plus B plus C plus D, and I will get the same answer. So let's try it. Let's do B and then D. So we go up B, and then we come back down D, and then we have to do A and C, and then we go A, and then we come back to C. So B plus D plus A plus C still gives us 0. We went up, down, left, or right, left, and we came back to the origin. Any way you do this, you can go dA, so I could start at the origin, go down D, go over A, up B, and over C. No matter what order of addition or subtraction, we'll talk about subtraction in a second, you do, it doesn't matter. You can do them in any order you want. Essentially, what this is saying is we can pick up our vectors and move them wherever we need them, wherever we want them, as long as we don't change their direction or magnitude. That's really, really helpful. That helps us do mathematical processes to them easily by putting them tip to tail or tail to tip as necessary to cancel things or to perform operations on them. One really, really important thing, though, is we've already said that if B upward is positive, then the same magnitude, 180 degrees opposite direction, is negative. That is subtraction. Subtraction in vectors, A plus negative B, is essentially A minus B. They're the same thing. However, there's a huge difference between A plus B and A plus minus B. And that's probably obvious to you, but let's look at it. So I'm going to call this R, and I'm going to call this R prime. So if I still have my same A, right, and I have my B, these are vectors. I'm not putting the vector signs. If that bothers you, I'm sorry. So A plus B is R. But now what about A plus minus B? So here's A, and now I take my minus B, and I notice that I put the tail of B at the tip of A, tail of minus B. And now notice R prime is actually in a different direction than R. It's actually 90 degrees off R. And it points down. And why does it point down? Well, it points down because the components of R prime are AX plus minus BY, right, in the X and Y. So the components here are 2X minus 2Y, right? And that gives us this resultant. In general, and therefore, when I get the magnitude of R prime will be 2 squared plus negative 2 squared. So the magnitude of R prime and the magnitude of R are the same, but their directions are very different. Tan of theta R prime, which this is theta R prime, is now R prime Y over R prime X, which is -1, which is -45 degrees. A little bit clearer on that, let's do this. So imagine instead I have a vector A and a vector B, and I don't care really where these angles are, but I can draw a resultant R, okay? And so I get that A plus B is equal to R. But now I want to take the negative of B. So here I would go A, and the negative of B is B in the opposite direction. And now my R prime, in fact, this is exactly what you're going to do in lab, negative R, let me call it R prime. And so now you see that A minus B is R prime. And you can tell from this picture that R and R prime have different magnitudes. They have different angles from the x-axis, completely different angles from the x-axis in these cases. So in general, even though subtraction is the same as adding a negative vector, subtracting a vector can give you a very, very different result. Vector addition and subtraction is commutative, meaning the order doesn't matter. But when you start to have negative signs, things become a mess. They're not the same. It's very, very different when you're doing subtraction, okay? And then the other thing to remember is that vectors work like triangles, right? So let's say we have A and B, and we're going to add these, but we're going to want to add these together. Let me not do that, sorry. Let's say I have a vector A, which is 30 degrees off the x-axis. And then I have a vector B, and B is 110 degrees off the x-axis, okay? And I want the components of these guys. Well, I know that A is AX plus AY, and let me say that A is, I don't know, 12, and B is 9. Okay, so this is A cos theta plus A sine theta. And if cosine of 30, so 12 cosine of 30 is 10.4. So this is 12 cos 30 plus 12 sine 30. This is 10.4 and 6. In the x hat direction, in the y hat direction. Now B, Bx and By, this is B cos theta plus B sine theta, where here this theta is 110. So this is 9 times cos 110 plus 9 times sine 110. And here you need to be careful because cosine is going to be negative here. Negative 308. And 8.46. Okay, so the idea here is that you would break, this would be By, and this would be, I'm sorry, Bx, and this would be By, and you would have, this would be B, that we've broken up into its Y and X components, right? And A, I can break up into AY and AX, sorry, AX. And so this is my A, right? And now, if I want to add them, right? I see that I have A, and then to add them, I have to put the tail of B at the tip of A. I know they're not drawn exactly the scale. Another way to see this is that I know that B, A of Y plus B of Y, and A of X plus B of X. Okay, so now in the X direction, I have that my resultant, which would be something like that, is A plus B. And that's equal to AX plus BX in the X hat direction, plus AY plus BY in the Y hat direction. And if I go back and look, my AX was 10.4. So this is 10.4 minus 3.08 in the X hat, plus 6 and 8.46 in the Y hat. And my resultant vector is 7.32 X hat plus 14.46 in the y hat. And it has a magnitude. I'm just going to do it in my calculator. 7.32 times 7.32 plus 14.46 times 14.46. Take the square root of this answer. I get 16.21. So the magnitude of R is 16.21, and arctan of Ry over Rx is the angle of R. So Ry over Rx is 14.46 divided by 7.32. Arctan of this answer is 63 degrees. This is arctan of 14.46 over 7.32, and that is equal to 63.15 degrees. So now I know that Ry and Rx look like that, and this angle of R is 63.15 degrees, and R has a magnitude of 16.21, whatever my units are. Okay, so I can take any two vectors, break them up into their components, which is what I did here, and then add those components to figure out what my radial vector is, which is the addition of those two. We've already done this next part, but essentially that's all you do. And you can do it with multiple vectors. I mean, you could have something crazy like A and B and C, right? And then find the radial vector from the tail of A to the tip of C, right? So here R would equal A plus B plus C. The only caution that I have for you is that when you start doing this, for some reason, people will try and do this, where they'll put them tail to tail. That doesn't work, because how are you supposed to draw a radial vector? You've got two different directions. They have to be either tail to tip or tip to tail. Another thing that people sometimes do is they'll draw it like this. And if you understand this, you'll understand everything. So if I draw this, if I walk, I get A. I'm walking backwards of B, and I'm walking that way of R, right? So I get minus R is equal to 0, or A minus B is equal to R. Is that right? Is that correct? Let me get rid of this for a minute, and let's look at that. So let's draw it the correct way and see what we get. Remember that instead of B, we can have minus B. And this is minus B, right? And this is R. Sorry, I don't really like that way I do that vector. So all I did was I flipped B around. I changed the direction by 180 degrees. And you can see that this is indeed A minus B, or A plus minus B is equal to R. So it's fine. This is actually okay. If you want to subtract B, you just put its tip to the tip of A, and then you draw the resultant from the origin or the tail of A to the tail of B. I think of it as walking. That I walk, if I walk in the direction of the vector from the tail to the tip, the vector is positive. If I walk from the tip to the tail, it's negative. Tip to the tail is negative. And so I can write A minus B minus R is equal to 0. Once I have this, though, that's only step one. Step two is to turn this into its components. And as you can see here, I may have to do some real work. If this is like 32 degrees to A and this is 110 degrees between A and B, you're going to have to do some real work there. We're not going to get into this too much, but think about this. Actually, we will get into that a little bit right now. Let me talk about this for a second. So let's say that I have A at 60 degrees. And then I know that this right here is, what would that be? 90, 30. This is 130 degrees, right? Is what I'm given, okay? There's 130 degrees between A and B, and I want to draw a, I want to know what R is. So this is my R. Okay, I know that A plus B is equal to R, but now I have a problem because I need to write A of X and A of Y and B of X and B of Y. And let's say this is 1 and this is 2. I don't really care. I just want some numbers to fill in. So this is 1 cos 60. And this is 1 sine of 60. And that's fine. But what is B? Because we're measuring B from the x-axis, okay? First of all, I want to show you this. So this is a 90-degree angle where A and B meet. This is therefore 30 degrees. So I know this is also a 90-degree angle. So my issue there is I know that 130 is equal to 30 plus 90 plus the angle of B with the x-axis. And that's what this is B cos angle of B and B sine angle of B, okay? So that means that this is 130 minus 120 is angle B, or it's 10 degrees. Okay, so this is B cos of 10 and B sine of 10. That will give me my R. Let's make sure we're correct. I said that B was 2. So this is 2 cos 10 is 1.97. This is 1.97. And 2 sine 10 is 0.35. And this is cos 60 is a half, 0.5, and sine 60 is 0.866. So if I add these together, my R has Rx plus Ry, sorry, which is Ax plus Bx in the x hat plus Ay plus By. In the y, and this would be Ax is a half, Bx is 1.97, so this would be 2.47 in the x, and 0.35 plus 0.866 is 1.216 in the y hat, which you can kind of see this looks like it's about that. If A goes here and B goes here, our vector is about 2 long and 1.2 high. That is going to give us our R. If we decompose R, we can see that Rx is about twice as long as Ry. Okay. You have to do a few of these problems so that you can get used to finding the angles that B is at sometimes. That's the real trick. We're going to do a few of these cases really fast. let's do this one that will be a little bit harder. All right, a little bit easier, I should say. A and B. A is initially at 45 degrees. They're both 5. This is 90 degrees off, so we need to know the components of A and B, and we need to find R. The first thing that we can do is draw a picture of R, right? But I want the magnitude and the angle of R. Okay, so A plus B is equal to R, and therefore R of X is going to be AX plus BX, and R of Y is going to be AY plus BY. And then I want the magnitude of R, which will be Rx squared plus Ry squared, and I want the angle that R makes. The angle of R will be arctan of Ry over Rx. So the first thing I have to find is what are the components of A, what are the components of B. AX and AY are obviously A cos 45, A sine 45. But what about B? So here's the angle that we need to know. What angle does B make? So this is going to be B cos angle of B, B sine angle of B. And let's look at this. From the x-axis, we have A is 45 degrees and B is 90 degrees. And what that tells us is that B is actually 100 and we can draw another parallel x-axis. We see that this is 90 degrees and we know this is 45. We know it's 45 because this angle is 45, this angle is 45, this angle is 45, and this angle is 45. So this whole angle, angle B, is 135. Another way to see that is it's negative 45. We don't need to really worry about that too much yet, but you can just write this as 5 cos of 135, or you could write it as negative cosine of 45 and sine of 45. Anyway, and this is 5 sine of 135. So these numbers are going to be the same. Cosine of 45 is 1 over root 2, okay? And so this is 5 over root 2, and this is also 5 over root 2. And it turns out that this is going to be negative 5 over root 2, and this is going to be 5 over root 2, okay? So if I do AX plus BX, AX is 5 over root 2, and BX is negative 5 over root 2. And this is 0. Obviously it's 0 because I'm going up 45 degrees, a magnitude of 5. Then I'm going the opposite way, in the opposite way, 135 degrees. I'm going to have no X component. X is going to be 0. This is going to be 2 times 5 over root 2, or 10 over root 2. Or if I multiply by root 2 over root 2, I get 5 root 2. So this is 5 root 2 in the y-hat direction. That is my magnitude because Rx is 0. So this is 5 root 2. And my angle, interestingly enough, Ry is 5 over root 2. This is arctan of 5 over 0. Tangent goes to infinity at 90 degrees. So if you try to put in arctan of some really big number, you see that you get 89.99999 degrees. That tells us that the angle of R, the angle that the R vector makes with the x-axis, is 90 degrees, which is actually easier to see from the picture and to know from Once you realize that you have no x component to our r vector, you should know that this thing's going to be at either 90 or minus 90. The beautiful thing about vectors is it's easier to see what's going on sometimes by drawing a picture. It's more useful. That's why we draw pictures in physics. So finally, this is an example in your book, and I just want to talk about, I'm going to do it a little bit different, but they talk about a plane flies 215 kilometers and at an angle of, let's say, 33 degrees. And we want to know how far north from where it started and how far east from where it started is. This, just to remember, is, this is our plane vector, and P of x is 215 cos of 33, and P of y, sorry, I wrote it. P of y is 215 or sine of 33. I'm not going to do that, but basically what you get is you get P of x and P of y. But another way to look at this is the same if I pick this guy up and I move it there. This is the same as py and px. So the resultant vector is really one thing that you can do. You can draw py, px, or you could draw a and b. And then you can also draw b and a and divide it up in two. This is the parallelogram theory of addition, right? If you switch the order of operations, the resultant is the line between them. It's not that useful. I don't know why you would do the full parallelogram when you can just do one part of it, but it's also easier for some people to see that in vector addition, that's really what you're doing, is you're adding the two components. Okay, so things to know: vectors have components. And when we add any two vectors, we add those components to get the new components, the components of the new vector. You need to be able to find the magnitude and components of a vector or a vector sum, meaning you need to be able to find them for A and B and for R. You need to find the resultant vector R. And you need to find the magnitude and direction of that resultant vector R. I should say here that you need to be able to draw that resultant vector. So if I have some crazy A down and some weird B going this way, right? And here's my origin, then my resultant goes from the origin to the tip of B. Just be able to draw that and add as many vectors as you want. You could have A, B, C, D, E, F, G, any order that they are. Just practice drawing the R vector. Have fun with it. They're like little puzzles. But that's what you need to know how to do. Make sure you know how to do those. So now we're on to vector multiplication again, and hopefully this will go pretty fast. So vector multiplication comes in because vectors are unusual objects. And in general, we have two types. We have dot and we have cross. And when dot occurs, dot is a lot more like normal multiplication. So if we have these two vectors, any two vectors, we have some A and we have some B. Let me not do that. Sorry. So I have A, which is along the x-axis, and I have B, which is along the y-axis, and I have some C, which is at some angle to the x-axis. But I have these two vectors, A and B. If I want to multiply them, what I do is I simply take A and B, I take their magnitudes, which we already talked about, and I multiply by the cosine of the angle between them. There's two special cases here. If A and B are along the same line, I'm going to back up for a second. When you multiply, unlike addition and subtraction, put them tail to tail. So let me back up and get rid of this for a minute. So when you multiply, you always put them tail to tail. So if I have, in this first example, A and B are both along the x-axis, and they're both actually the same magnitude in this particular case. The angle between them is 0. If I put them tail to tail, right? They lie along the same line. What if they are in opposite directions? Okay. So this is B and this is A, and the angle between them would be 180 degrees. Cosine of 180 degrees is negative. So if AB is 0, if AB is 180, so in the second case, I would get AB, I would get negative AB, okay? And in fact, if A and B were exactly the same magnitude, this would just be A squared. This would be negative A squared. So when you're multiplying two vectors in the same direction, if they are anti-parallel, meaning opposite directions, you get a product of them that is negative. And if they're in the same direction, you get their product, but it's positive, okay? And also, it doesn't matter what order in dot product you do. The last thing you have to know is the product is going to be a scalar. It's just going to be a number, which is a little weird, a little hard to wrap your head around. But you multiply two vectors and you just get a pure number. Often it's an energy or something like that. So a second thing to do is that you can multiply the components. So when we're multiplying our A and B, right? Notice that A of X and B of X, A of X here is A, and B of X is minus B in the X hat direction, in the X hat direction. So therefore, we get a negative quantity. We can have a negative scalar result of a dot product. That's okay. You can have negative work. You can have negative energy. It means something, and we'll talk about that later. But for a dot product, all you do is you multiply each individual component, add them all together, and that is your result. And your result is just a number. Now notice another case that can happen is if B and A are perpendicular. So they're 90 degrees off each other. We go back and look at this. If AB cos 90, cos of 90 is 0. So when they're perpendicular, you get nothing. Another way to state that is that A of X is A and A of Y is 0. B of X is 0 and B of Y is B. So what we'd have when we dot them, so we'd have A times 0 plus 0 times B, and we get nothing. The reason why is what the dot product's trying to give you, or what you're getting out of the dot product, is you're getting what's called the projection of B on A, or A on B. I'm going to show you that in a second, but when we put, let's say A is along the x-axis and B is at some angle, okay? The dot product, A dotted with B, is A, B cos theta, where theta is the angle between them here. And you can imagine that B of X is equal to B cos theta. So in a sense, what you're doing is kind of the shadow of B falling on A, the amount of B in the same direction as A, or the projection of B onto A is your dot product. It tells you how much the two vectors are reinforcing each other and how much of the vector is perpendicular to A. How much of B is parallel to A, how much of perpendicular? We'll talk about that in a minute. It's commutative because it doesn't matter if we do B dotted with A or A dotted with B. Cross product is not commutative, but the dot product is. We can do it in any order we want. So we've already done the example of A dotted with A gives you A squared, and A dotted with negative A gives you negative A squared, right? So if they're 90 degrees and A dotted with B, if B is perpendicular is equal to 0. So if they're 90 degrees off each other, it's 0. And lastly, A dot B is equal to B dot A. Those are all well and good. Let's actually do a couple of useful examples. So those of you who have had physics already will know this. This is a pretty common example, but there's something called work, and work is actually how much energy you put into a system. If you've taken thermo and chemistry, you probably know that. But work is how far you push something dotted with the force that you're applying, okay? So if I try to push a box, I'm a human and I'm pushing this box with some force, right? And it travels some distance r. Then I dot r dotted with F is, since r and F are in the same direction, cos theta. Now, however, let's say I carry a book along r and the force of gravity acting on that book is down. So I'm holding the book in my hand and I'm walking across a room. And the length of that room is my r vector. While I'm holding that book, the force of gravity is acting downward. And these two forces have an angle of 90 degrees, actually negative 90 degrees. So the work done here is the dot product of r and F, and that's r F cos of 90 or negative 90. And this whole thing is 0 because cos of 90 or negative 90 is 0. Therefore, we say that when you carry something across a room, if you don't speed up or slow down, you actually don't do any work. And the reason why you don't do any work is the dot product between the displacement of the book, that vector, and the vector of the force of gravity. Since they're perpendicular, they can't possibly be doing any work. Another way to see this is, and this is probably better, if you're pushing on a block, let's say, okay? You're pushing upward at 40 degrees with a force, and the block is sliding. How much are you helping? How much of your force is actually pushing and how much is pushing up? So your force has a force in the x, which is F cos 40, and a force in the y, which is F sine 40, and your r vector. So r dot F is, the r vector is only in the x direction. You will get rx times fx in the x, nope, plus ry in the fy. Now let's say our force is 90 newtons and our r is 5 meters, okay? So rx is 5. And this is 90 cos 40, which is about 69 newtons. And 90 sine 40 is about 57.9 newtons, okay? So here, our product is 5 times, what is f of x? 69 plus 0 times 57.9. This part goes away, and we get 345. This would actually be joules, it's energy, but you don't need to know that now at this point. So basically, only the part of the force in the direction that you're pushing the block, or in the direction that the block is traveling, does work. The part of the force, so part of this force is parallel to the direction of travel, and part of it is perpendicular. And that perpendicular part of the force doesn't help at all. It just kind of lifts it, but it doesn't help it move. So a dot product is useful when you want to know how much two vectors are influencing each other. It's the product of two vectors in the same direction. Now, that doesn't mean that you can't have coordinates in both directions. R could be at some angle too, and you would have Rx and Ry. And at that point, you would have to figure out the coordinates of, or the components of R as well. But when you added them all up, you would just get a pure number. There's no direction to F dot R. It's a number. A dot product doesn't have direction. It becomes a scalar, okay? And when we multiply, onto the cross product. So the cross product is the opposite or different than the dot product. In the cross product, when we have A and B, right? A and B, what we actually do, let me actually switch those for reasons that will become apparent later. But so I have a vector A and a vector B, and A lies along the x-axis again, and B is some angle between A and B off of A and the x-axis. So if A and B only have components in the x and y direction, in 2 dimensions, A cross B is actually this. You're multiplying the perpendicular components. It, however, is equal to the magnitude of A times the magnitude of B times sine of the angle between A and B. I'll usually write this as a theta, but I wrote it as, or as a phi, but I wrote it as theta in there. So the resulting vector is actually perpendicular. That's what this part says. If you only have components in the x and y, you end up with a vector after you do the multiplication. You end up with a vector in the z direction. If it's positive z, you need to understand that if x is this and y is positive this, z comes out of the page towards you. I'm drawing it like that, but z comes out of the page toward you. That's a right-hand coordinate system, because if you move x to y with your right hand, you turn your fingers, you curl your fingers from x to y, your thumb points at you or out of the page. This can obviously be positive or negative depending on what the components of A and B are. Here, A only has an x, so that would all go away. And we can see that that's rotating. We'll talk about that in a second. The sign of Z actually denotes whether or not it's clockwise or counterclockwise. And there's a couple of ways you can do this that we'll practice. So the cross product actually comes from something called a determinant of a matrix of the 2 vectors. If you have A is a vector with AX and AY and AZ, and B actually has 3 components as well. For those of you who know what I'm talking about, this is useful. If you don't know yet, that's okay. I'm going to write this as X, Y, and Z. and AX and BX and AY and BY and AZ and BZ. And then when I do a determinant, what I actually do, so the determinant of this, which is the cross product, you take the first, this first, and then you take the cross of these two. So I would do AY times BZ minus this cross, BYAZ, and that gives me my X hat coordinate. And then I add it. I'm going to do these for Y. I basically block off these two and I do AXBZ, BXAZ. However, every other column, you have to add a negative sign. I'm just going to flip it. So BXAZ minus AXBZ is my Y hat. And finally, Z. AXBY minus BXAY is my Z. And that gives me what the cross product is, for those of you who have had matrices. Notice that if I didn't have a Z component to these vectors, everything in the X hat and the Y hat direction would be gone, because every one of these depends on a Z coordinate, and I would just be left with the bottom, which is exactly what I had here. So in 2 dimensions, if there's no Z component to the vectors, you only get a Z component to the cross product because everything else has a Z component in it. What this is really saying is this long thing here. What it's really saying is that you multiply the perpendicular components, and that gives you a perpendicular rotation. Cross products are rotations. They are actually vectors. And because they're rotations, you have to be really clear and think about this. But first of all, let's do a couple. A and B are on top of each other. Remember that A cross B is A, B, sine of the angle between them. Sine of 0 is 0. This cross product is 0. And B cross A is also 0 here. However, A and B here, notice that AX, there is no AY. So if we go back and look, this is positive. So A cross B here is AX BY. There is no AY. AY is 0. So we're crossing, we're turning A to B, and we're getting in the Z hat direction A times BY, AX times BY. Now, if I do the opposite, and I'm going to do it up here, I'm going to draw it up here. So B, and I'm trying to turn B to A. So I'm doing B cross A, right? What I actually get, and this is really important, is they flip. If I'm crossing B, I get BXAY minus BYAX in the Z hat. And note that these vectors are still the same, but, and I'll draw it down here just for, I'm trying to cross B to A. AX, A only has an X component still. So when I'm crossing B to X, I get BYAX. And when I'm crossing A to B, I get AXBY. And what this leads to is the general idea that A cross B is equal to negative B cross A. Now, if you look at this picture, I want to talk about one thing really fast. You already know a right-hand coordinate system. Once you've done algebra for a number of years, you realize that when you turn this, when you turn from the x-axis to the y-axis, you turn positive angles. What we're trying to do is we're trying to rotate angle A, or vector A, to B. We're trying to turn the, we're placing A and B tip to tip, or tail to tail, and we're trying to rotate A, the tip of A, to the tip of B. we see that that's a positive rotation. And indeed, when we did A cross B, we got positive A x by was our answer. However, if you were to try to go down, if you were rotating clockwise, you would get a negative angle, right? Rotating down from the x-axis. And here, if we're going to try to cross B to A, we're trying to turn the tip of B to the tip of A. And we're doing it in a negative direction. And the math tells us that we get negative AX BY. I should put that these are in the Z direction. The weird thing here is that we call this rotation as if it were in the Z direction. Basically take your right hand and curl your fingers into your palm with your thumb sticking out. Point your thumb at yourself and curl your fingers into your palm, right hand. And you see that you curl in the same direction as positive rotation. If you stick your hand out and point your thumb at your screen, in your thumb, your fingers curl of your right hand, curl in the negative direction, that's negative rotation. Because we're in a right hand coordinate system, this is the same as negative Z hat. This is the same as positive Z hat, positive Z. You've also seen this as Z, Y, X. So this is the same as if we were looking at it down, we were here and we're looking that way. And this is the same as if we're looking at it, but it negative Z. A better example of this, if you've ever tried to turn a wrench, okay? So you're trying to turn a wrench. If this distance is my R, and the force I'm applying is up, okay? Now, if I pull on it, so my force 1, my pull force, R cross F is RF, sine of the angle between R and F. If I pull on a wrench, what happens? I'm unable to turn it. I don't do anything. I'm trying to turn a bolt. If I push up, and this is my force 1, and my force 2 will be force 2. If I pull up, R and F1, R cross F1 is, let's look at it, R and F1. I put them tail to tail, and I rotate R to F. I get positive R F1 because the angle between them is 90 degrees. And RF sine of that angle, sine of 90 is RF1. If I try to rotate it F2, which I'm going to do here, so my R and my F2, I'm rotating negative. So I get negative R F2. And that's because the angle between R and F2 is negative 90 degrees. And sine of negative 90 degrees is negative 1. All right, so if I try to push down on a wrench, in this picture, I'm pushing down with force 2, I get a clockwise or negative rotation. If I try to pull up on it with F1, right, I get a counterclockwise or positive rotation. That's what the cross product is telling you. You have two vectors. This is actually called torque, and we're going to do it much later. But when you have two vectors, if you cross them, you get a rotation. You can only get a rotation if they are not parallel. If they're parallel, you'll never, ever get it. And this is the right-hand rule. We've already gone over this. So the final thing I want to talk about is the mathematical properties of vector products. Okay, so we can do some weird combinations of A dot B cross C dot D, right? You can do all these weird things. In fact, there's something called a triple product, which gives you the volume of an object. But I want you to make sure that you'll learn all that in vector analysis or in Calc 3 or whenever you learn it. I want to make sure that you understand the dot product A dot B gives you a scalar, okay? And you can always dot a vector with itself. You get A squared. Dot products are commutative, which means you can, A dot B is equal to B dot A. However, for the cross product, you cannot cross a vector with itself. Why? Because they're parallel to each other. A and A are parallel. The angle between A and A would be 0, and A cross A is AA sine of 0, which is 0. So you can't really cross a vector. You can. There's reasons why you may want to do that for some odd reason in derivations and stuff. But if you cross a vector with itself, you get 0. Cross products can only be performed between vectors. So A and B have to be a vector. You can't cross a scalar. What does it even mean? Multiplying a scalar by a vector makes sense. You're doubling the magnitude. Multiplying or crossing a vector and a scalar makes no sense because you don't have a direction to cause the rotation. You wouldn't know which way it would rotate, right? Because the scalar has no direction. And the cross product is not commutative, meaning A cross B doesn't equal B cross A. It in fact equals negative B cross A. So finally here, I want to ask you which equations here make sense. So let's go through this really fast and see what we get. In the parentheses, we get a vector. We get a vector, we get a scalar, and we get a scalar. Can I dot a vector and a vector? Yes, this one does. So I would get the product of B cross C, and I would dot it with A. Here, I have a vector, and I'm crossing them. So this one's fine. I can totally do that. I cross these, I get a vector, and then I cross that again with A. Here, I'm trying to cross a vector and a scalar. I cannot do that. This, in the parentheses, I would do first, and I would get a scalar out of that dot product. Here, I would get a vector dotted with a scalar. So yes, I can. I can always dot a vector and a scalar. So one of these you can't do. And when you take vector analysis or you study vector products in calculus, you'll learn that the triple product, I believe, is always written as A dotted with B cross X or B cross C. And in fact, there's a whole bunch of identities that you can use. But yeah, it's obvious what's going on when you realize whether your product is a scalar or a vector, what operations are allowed. And you don't actually even need parentheses because there's only one way you can do it. If I look at this, if I give you A cross B dot C, you know you have to do this first because you can't dot B and C, you get a scalar. But anyway, so that's vectors and essentially a little bit on chapter 1. I'm going to give you some homework later today on this that you can go through and do. Read the chapter, make sure you know how to add and subtract vectors and what those things mean. Know how to break a vector into components, and you know how to do the dot product, and you know how to do the cross product for 2 dimensions. Anyway, I'll talk to you all later.